The National Electrical Code, or NEC, outlines specific guidelines for overcurrent protection in electrical systems. These requirements differ based on voltage levels, particularly when comparing cables rated for 600 volts or less versus those rated over 600 volts. While the language addressing cables over 600 volts may appear less restrictive, adhering to these regulations is critical for ensuring electrical safety and preventing equipment damage. Article 240.100 addresses the fundamental requirement for overcurrent protective devices. This section mandates that these devices must reliably detect and interrupt any current exceeding their set trip points. In simpler terms, the protective device, be it a fuse or a circuit breaker, must be capable of quickly clearing a short circuit fault at any point within the circuit it protects. This ensures that any excessive current due to a fault is rapidly cut off, preventing potential hazards like fires or equipment damage. Article 240.100 focuses on preventing excessive temperatures caused by short-circuit currents. While it doesn't directly address overload conditions, it highlights the importance of protecting against thermal damage resulting from high fault current. Other articles in the NEC provide additional guidance on overload protection, complementing the requirements of 240.100. Article 240.101 provides specific guidelines for sizing overcurrent protection devices. It allows fuses to be sized up to 3 times the cable's ampacity rating. For circuit breakers, the long-time trip element setting can be set up to 6 times the cable's ampacity rating. This seemingly higher allowance is based on the intended function of these devices, which is to primarily protect against short-circuit faults, not overload conditions. Overloads, which involve currents exceeding the cable's ampacity for extended periods, are addressed separately through other NEC provisions. To illustrate these concepts, consider a 2/0 copper type MV-90 cable with an ampacity rating of 200 amps. According to Article 240.101, this cable could be protected by a circuit breaker with a long-time trip element setting of up to 1200 amps. This might seem counterintuitive at first, but it aligns with the understanding that the circuit breaker's primary role is to interrupt high-magnitude short-circuit currents. However, it's crucial to emphasize that the continuous load current on this cable should never exceed its 200 amp ampacity rating. Allowing continuous current above this rating can lead to overheating and potential damage regardless of the circuit breaker's trip setting. It's important to clarify that Article 240.101 does not permit damaging temperatures in the cable due to continuous load current. Article 310.15, along with its associated tables, addresses conductor ampacity and temperature limitations. It dictates that the allowable ampacity of a conductor must ensure that its temperature rise does not exceed the insulation-specified limitations. Overcurrent protective devices are not designed to protect against overloads caused by continuous load current. Instead, other measures, like proper conductor sizing and load management, are necessary to prevent overloads and maintain safe operating temperatures. Therefore, while the NEC may appear to permit higher overcurrent settings for cables over 600 volts, it is essential to ensure they receive adequate protection. Overcurrent protective devices should be sized to trip in the event of a short-circuit fault, and continuous load current should always remain below the cable's ampacity rating. Understanding the difference between short-circuit and overload protection is key to applying these rules effectively. Short circuits involve very high currents that can quickly damage equipment and cause fires. Overloads, on the other hand, involve currents that are moderately higher than the cable's ampacity but can still cause overheating and insulation degradation over time. Proper overcurrent protection strategies address both of these scenarios to ensure a safe and reliable electrical system. In summary, navigating the NEC requirements for overcurrent protection of cables over 600 volts requires a thorough understanding of Articles 240.100 and 240.101, as well as related provisions in Article 310.15. By correctly applying these rules, electrical professionals can ensure that high-voltage cables are adequately protected against both short-circuit and overload conditions, contributing to a safer and more reliable electrical infrastructure. Furthermore, it's worth noting that the specific requirements for overcurrent protection can vary based on the application and the type of equipment being protected. For example, motor circuits often have different overcurrent protection requirements compared to general lighting or receptacle circuits. Consulting the relevant sections of the NEC that pertain to specific equipment is crucial for ensuring code compliance and proper protection. Remember that electrical codes are updated regularly, so staying current with the latest edition of the NEC is essential for all electrical professionals. Changes in the code can affect the allowable overcurrent protection settings, conductor ampacities, and other critical aspects of electrical system design and installation. Ongoing education and training are vital for maintaining proficiency in electrical safety and code compliance. When selecting overcurrent protective devices, it's important to consider factors such as the interrupting rating, which is the maximum fault current that the device can safely interrupt. The interrupting rating must be sufficient for the available fault current at the point of installation. Using a device with an insufficient interrupting rating can lead to catastrophic failure in the event of a short circuit. Another important consideration is the coordination of overcurrent protective devices in a system. Selective coordination ensures that only the overcurrent device closest to the fault trips, minimizing the impact on the rest of the system. Improper coordination can lead to nuisance tripping and unnecessary downtime. Moreover, the type of load being served can also influence the selection of overcurrent protective devices. For example, inductive loads like motors can draw high inrush currents when starting, requiring the use of time delay fuses or circuit breakers with specific trip characteristics to prevent nuisance tripping. Understanding the characteristics of the load is essential for selecting the appropriate overcurrent protection. In addition to the NEC requirements, other industry standards and best practices can provide further guidance on overcurrent protection. Organizations like the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, publish standards and guides that offer valuable insights into electrical safety and system design. Consulting these resources can enhance the effectiveness of overcurrent protection strategies. Ultimately, the goal of overcurrent protection is to safeguard electrical systems and personnel from the hazards of excessive current. By adhering to the NEC requirements, staying informed about industry best practices, and carefully considering the specific application, electrical professionals can create safer and more reliable electrical installations. Keep in mind that this information is for educational purposes and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or electrical engineer for specific guidance on electrical system design and installation. Continuous load current should always be below the cable's ampacity rating.